Hello and welcome guys to another session in the Mind Grid. Today we're talking about a high school physics problem about velocity time graphs. Just recently, one of my kids was working through some physics problems and I happened to be watching her solve the problem, and somehow um, when she asked me the problem, I had to think about it a little bit, and that made me wonder, since I have a programming background, uh, if I could use Python to do a simulation on this problem. So I ended up creating a small Python program using ChatGPT, and I would like to share that with you. And let's go. So the basic problem for the ramp and ball is that there is a ball that is moving at some initial velocity in this case, and with this velocity it starts climbing the ramp, and we want to plot the velocity time, the displacement time, acceleration time graphs, etc. for the motion of this ball. But we have to kind of keep in mind there's no friction in this case, because friction could complicate things. So there's no friction, and there is a ramp length, maybe a ramp angle is given in some cases, but really they could just say constant acceleration or something like that. So the usual thing is, at an early stage, you may not be aware of exactly how gravity is causing the deceleration or acceleration on this ball. But essentially, the force of gravity, if I can just draw it here, the force of gravity is acting on this ball all the time, and the force of gravity is pulling you down towards the center of the earth with um, some acceleration g, right? So as the ball climbs on this ramp, there is an acceleration of g that goes down this way, but there is a component of this acceleration that goes along this line, and that is the component that will act on this ball, because the component that goes in this direction, you will not feel it because there'll be an action reaction from the ground, so this will cancel out. But the one that will slow you down is this component of g. So if you have not studied it, eventually you will understand that based on the angle theta here, you can calculate this acceleration or deceleration on this ball. That deceleration turns out to be a constant value based on the angle of the ramp and the gravity, the acceleration value, which is 9.8 meters per second square. So as this ball climbs up, obviously we have to simulate this using the fact that there is a constant acceleration downwards on this ball, and the initial velocity is 5 meters per second in this simulation. The ramp length we've assumed to be 10 meters, ramp angle is 30 degrees. And the mass of the ball is given here, but it's not really relevant because none of the equations of motion really need it. All we need is the acceleration, and we know that the acceleration is the same on all objects irrespective of their mass. The gravity acceleration is the same. So that being said, I guess then I moved on to simulate this. And so my first simulation was with this initial speed of 5 meters per second. The ramp length obviously was 10 meters and the ramp angle was 30 degrees. So in this case, what I found out was that as the ball moves up, it's obviously starting off at 5 meters per second, but here you can see that at time equals 1, the ball has a velocity of 0, right? And then thereafter it starts to get a negative velocity and keeps speeding up. The velocity increases in this direction, right? So this is a linear velocity time graph. You can see that the ball kind of slowing down because of gravity. The ball, this is displacement time graph, and you can see the velocity is the slope of this, and so you can see the velocity is kind of slowing down and it becomes exactly 0 at the top here, which coincides with this point where we can see velocity is 0. Velocity is basically 0 here. We can see that from the displacement time graph. And then the ball starts to accelerate downwards and crosses here at this, you can see the velocity, whatever this velocity is, negative 5. As it comes down the ramp, it's exactly -5 here. So it's basically rolled down the ramp because the ramp's too big, right? Because it only climbed up 2.5 meters off the 10-meter ramp, right? So it didn't climb very far up, and it rolled back down. The acceleration, obviously, because the ramp has constant acceleration, you can see that the acceleration is always the same value because you're still on the ramp, right? So the point is, as long as you are on this ramp, the ball will experience constant acceleration in this direction, which is, some function of gravity, right? G sine theta. So this will always act on you. It's only when you go past this point that the ramp ends, and then the gravity acceleration or deceleration stops acting on it, because see, the gravity is still acting on you, but the gravity at this point is downwards, and because of the ground, there's a reaction that is going upwards, and so these two cancel out, so there is really no gravity acting on this ball at that point. So as soon as it crosses the ramp, the acceleration goes away, and we'll see in the next example how that impacts it. But here in this example, you know that the ball's falling down. You can see the velocity time graph kind of looks like that. Your velocity is high at the bottom and then slowly goes down to 0, and the ramp is still, you only covered small parts of the ramp. You're like here somewhere, and your velocity has become 0, so you're going to roll down. Obviously, under gravity's effect, you're just going to roll down, and the acceleration is that constant -4.9, and so based on that, you're just going to fall down, right? So now let's take a look at a different example. Now take a look at the example where initial speed is 10 meters per second. So in this case, if you're too fast, as you roll this ball up, it's too fast. So what you can see is that the velocity decreases, but it does not decrease all the way down to 0. It reaches some small value here, and then it has reached the end of the ramp, and you see that the effect of gravity has gone away because you see the acceleration became 0 from this point onwards. If the acceleration is 0, the velocity just goes on at that constant trajectory. So velocity time graph shows from this point onwards is that constant angle, and the velocity time graph will show you that the velocity just becomes that value because there is no deceleration or negative acceleration acting, no gravity acting on it anymore, and so the velocity just remains the same. It's constant velocity at that point. Acceleration is 0, in other words, and so that's the outcome here. Now I'm going to show you real quick how the simulation actually took place, and if you need the code, I'm happy to provide you the code. In fact, I might just add it to the description of the video. But here you can see that there's two mathematical packages used. One is numpy, which is a numerical library, and matplotlib, which is a plotting function which helps you plot figures. Now these are the parameters for the simulation. The mass, which, like I said, it's not going to be used. You can ignore it. Mass is not really needed for this problem. The gravity is assumed to be 9.81 meters per second square, and combined with the ramp angle, we're going to compute an acceleration, but you could assume some acceleration. You could, in the problem, you could be given an acceleration, because the acceleration till you're on the ramp is always a constant, and it's acting downwards. The initial speed is input here as 5 meters per second. Ramp length is 10 meters. dt is basically the simulation step, so we're going to increase the simulation time by that dt and compute the velocity, acceleration, and the distance, displacement, and the Tmax is 5 seconds here. So first thing we do is we compute gravity by computing the angle in radians, and then the sine of that angle times the gravity, which is 9.81, and it's obviously negative because the force is acting downwards, which is the reverse of the direction of motion in this case. So it's very important to not miss that sign. It's very important to do that. And then we create arrays. And these arrays are held in place because we just compute for every time step. We increase the time by a small amount, which is shown here. And then for that time, we calculate, the position, velocity, and acceleration so we can plot it, right? And the initial condition for these are x equals 0, v is equal to initial speed, and t equals 0. So with that, now this is our main simulation loop, right? This is going to be our simulation loop. While time is less than t max, if x is less than the ramp length, then we just use two simple equations. V equals v0, which is the starting point of that simulation. Now in this case, because velocity has already been added and it has become from the previous time step, we just take the value, so it's the same v plus a times dt, x equals x plus v times dt, and t equals t plus dt. So we just keep incrementing time steps and computing velocity and displacement at each point. Now if the ramp length is exceeded, you can see that the velocity becomes constant, the acceleration becomes 0, and the x is the only thing that changes. So if you were to cross the ramp and reach out the flat part on the other side of the ramp, then you know that the velocity will become constant and the distance will just increase perpetually, right? Assuming there's no friction, so it's just going to keep going. Now if the ball rolls back down, this is the catch, that if you ever go to a point where x is less than 0, then the simulation will stop automatically. So the ball will just roll down the loop, the ramp, and then it'll stop. And that's the simulation. Although the ball is not going to stop, it's just going to go backwards in the other direction, but the simulation will stop at that point. So you'll never see the graph going negative in the x direction. So now at each step, we're just going to append these to the list, and we'll keep, for every time step, we'll keep its position, velocity, and acceleration. And at the end of this simulation, if we check that the position that we computed last is greater than the ramp length, then the ball has crossed over the ramp. If not, then the ball has rolled back down. So that is the simulation, and then we can just basically plot. So we comprise a diagram which has 3 subplots, right? And we provide some figure size, and then for each of the plot, we basically plot whatever we want to plot. So time versus velocity, time versus positions, time versus acceleration. This is how you can do it. You can plot any number of variables, just keep changing how many subplots you need, and just plot them this way. And then you do a layout of these plots and then save figure as PNG file, and you're done. So pretty much with this, what we ended up getting was these diagrams, and the simulation then plots all these values. You can see them, you can plot them, you can change the problem by changing basically this part of the loop. Like if you have a different problem where there are different set of conditions. In our case, there's this ramp length, but if you have a more complex trajectory, a more complex situation, or 2 cars or something, if you have problems like that, obviously if you can provide me a problem, I can provide you a simulation. It is also possible that ChatGPT can give you some of these Python simulations. Now for running these simulations, you need to be able to run Python on your machine. You may be able to run Python online as well, but if you have access to Python, I would highly recommend that you look at this video and study it, and make sure you can try some of these things on your machine, your laptop, or in your school if you want to try it and see if this makes sense to you. Now, the good thing about doing Python based simulations is that it's free. Everybody has access to these tools, and then if you run it, you can try various things, changing the speeds, changing the length of the ramp, all those things. You can see the impact of those variables on the outcome. And so with that, I'm going to stop here, And I just want to say that if you have any other problems, please feel free to reach out to me in the comments section. You can provide me those problems, and I'm happy to work out a solution for you and give you some insight and intuition into the problems. So that's it for today, guys. Until next time, take care and bye-bye.